Welcome to this lecture series in number theory. In this lecture, we'll look at some important results about GCD, which will be applications of Bézout's theorem. So let's recall. Bézout's theorem says that if we have two integers a and b, not both of which are 0, so that their GCD is defined, the theorem says that then there exist integers x and y such that the corresponding integer linear combination, as we call it, of a and b is the GCD of a and b. Okay? And this is another way to write the same thing. This whole pink statement can be written in one shot in this language. Okay? So GCD can be expressed as an integer linear combination. And a special case of Bézout's theorem, which is of particular interest, is that if two integers are given, not both of them are 0, then the relative primality of the two is the equivalent to the existence of integers x and y, which satisfy this equation. So you can express 1 as an integer linear combination of a and b if and only if a and b are relatively prime. Okay, so we will make use of these things, and we have seen these things before, and today we will put them to use. Okay. One problem for practice. And now let us get started. So the first property of GCD we are going to prove is the following. Suppose we have two integers a and b, not both of them are 0. And suppose there is some positive integer d which divides both of them. Okay, so here I'm taking d as some positive integer which divides both a and b. Then you can express the GCD of a and b as d times the GCD of the numbers that you get when you divide both a and b by d. So you can kind of pull out a divisor and take the GCD of the remaining. That's kind of what this is saying, right? It should be intuitively obvious. This statement should be intuitively obvious, but it takes a little bit of reasoning. Okay. So let's see. First thing I want to say is that d times GCD of a by d and b by d, this thing is a common divisor of a and b. So the reason is, whatever be the GCD of a by d and b by d, call it e divides a by d and e divides b by d. And thus de divides a and de divides b. So de is a common divisor of a and b, right? de is this. So this is a common divisor of a and b, and hence it cannot be more than the GCD of a and b. Right, so I hope this reasoning is clear. Call this e, then e divides a by d, and hence de divides a, which just means that this thing divides a. Similarly, this thing also divides b, therefore it is a common divisor of a and b, and hence it cannot be more than the greatest common divisor of a and b. So we have this, but now for the other direction, by Bézout's theorem, this times, let's call that, I think x is fine. So this times x plus b by d times y is GCD of a by d comma b by d. So what I really should be writing is that there exist integers x and y such that this happens, but I am being a little sloppy. So we know by Bézout's theorem that there exist integers x and y such that this equation holds. Now multiply by d on both sides. We get this equation, but the GCD of a and b, GCD of a and b divides the LHS of this above equation. GCD of A and B divides both A and B, and hence it divides the left-hand side, and therefore it also divides the right-hand side, and hence it cannot be more than the right-hand side. Okay, but now if we combine these two inequalities, we get what we wanted to prove. A very simple result, but still we made use of Bezout's theorem. Maybe you can avoid Bezout's theorem in proving this, but whatever. And let's see a small application or example of it. Some use of this statement. So suppose we are given that A and B are relatively prime. We want to show that the GCD of A plus B and A minus B is either 1 or 2. Right? So here is the proof, and I encourage you to do it yourself. I encourage you to prove everything yourself in this lecture and in any lecture. But do not skip the proofs that I am discussing, because they may have some value still. So start with the common divisor of A plus B and A minus B. Start with a common divisor of them, then it follows that D divides both 2A and 2B. Why is that? If D divides these two numbers, then it also divides their sum. Their sum is twice of A, and therefore it also divides, by the same reasoning, it divides twice of B, because twice of B is the difference of these two numbers. So we have D divides these two things, and hence D cannot be more than the GCD of 2A and 2B. But now use the scaling property. We get that, but since GCD of A and B is 1, we can just erase this. So therefore you pick any positive common divisor of A plus B and A minus B, you find that it is at most 2, and therefore the GCD is either 1 or 2. Right? And 2 may happen. It's not like it is necessarily 1. For example, if you pick 3 and 5, A as 3 and B as 5, the GCD of 3 and 5 is 1, but the GCD of 8 and 2 is 2, not 1. So you can't improve this result. Okay, great. A corollary of it is that if you have a common divisor of A and B, not just that it is at most the greatest common divisor, that's a triviality, it will also divide the greatest common divisor. It's immediate from this equation. D is a common divisor of A and B. This is obviously an integer. D therefore divides the GCD of A and B. So very important. Any common divisor of A and B is a divisor of the GCD, and conversely, any divisor of the GCD is a common divisor of A and B. So fine, great. Now for what I call the associativity property. Yeah, so we want to show that you can associate the brackets in whatever way you want. You have 3 numbers, A, B, and C. Let's say all of them are positive, though they need not be. It's just that no 2 of them are 0, so that you can talk about GCDs. Okay, great. So then we are saying that you can take GCD of the last 2 and then take the GCD of the first with that, or you can do it the other way. Naturally, this is called associativity. Just like we have associativity of addition. This kind of thing is called associativity of addition. We have associativity of GCD. Okay, so let's prove this. So let's say G is the GCD of A and B, or maybe, I don't know what notation I'm going to use. G be the GCD of A and B, and H be the GCD of B and C. Okay. Now, so we want to prove this equality. This will come, but let's first just talk about this one. So fix a common divisor of A and H. Positive common divisor. Okay. So then, by the previous property or previous corollary, Well, D divides A we already have, but then we also have the D divides B and D divides C. Why? Because if D divides H, D divides the GCD of B and C, and hence it divides B and it also divides C. Well, for this we don't even need the previous corollary, we just need the definition of GCD. If something divides the GCD of two numbers, it is naturally going to divide the two numbers because the GCD divides the two numbers. So far we haven't made use of this corollary, but now that we have this, we will make use of the corollary and say that D divides G and D divides C. Right? D divides A and B implies that D divides the GCD of A and B. So we have that, which means that D is at most the GCD of G and C. So what are we saying? D is at most this number is all we are saying. This is precisely that number. So if you pick a common divisor of these two numbers, you find that it is at most that number. Right? And you can do the converse. You can pick a common divisor of these two numbers and find that it will be at most that. So that shows that the GCDs of these two and those two are equal. Right? I hope that is convincing. The first piece of reasoning, whatever you have done, just shows this inequality. You just do the analogous reasoning, you get that inequality. So this inequality has been justified. For the last one, why should we believe this? Well, again, suppose you pick a common divisor of these two numbers. Then we saw that it is a common divisor of these three. So it is clear that the GCD written over here is at most that thing. And you can just do the same reasoning again. You pick a common divisor of these three people, you will find that it is a common divisor of GCD of A and B and that of C. And therefore it is at most that. So it's the same reasoning, there is no difference. Okay, so we have proven the associativity property. I did go a little bit faster, but I hope I have said it in sufficient detail for you to not be confused. At any rate, stay on it if it is unclear. You'll definitely get it. Very important associativity property. Okay. Now for something that I call the clubbing property. So what do we have? We have A and B are relatively prime. We have A and C are relatively prime. Then we are saying that A and BC will be relatively prime. The product of B and C cannot conspire to somehow create a common factor with A. If the individual components do not have a common factor with A, non-trivial common factor I mean, then their product will not magically create one. This is again intuitively very obvious but a nightmare to prove. Thankfully, Bezout's theorem makes it very easy. Okay, so let's show this result. So by Bezout's theorem, we have this is one for some x and y, some integers x and y, and we also have let's say alpha and beta. Sorry, this is a C for some integers alpha and beta. So everything is an integer. Here every symbol is an integer. And when I say ax plus by equals 1, I mean for some x and y, and here I mean for some alpha and beta. Okay, immediate from this and from Bezout's theorem, so we can write this. But now we product these two equations out. So this implies that the product, this is 1, right? If these two equations hold, then multiplying their LHS will be equal to the product of their RHS, clearly. Now we open the brackets as we do. So you get something like, when I don't want to spend too much time on this, but okay, let's do it in full. A square alpha plus ACX beta plus AB alpha y plus BC beta y. This is equal to 1. So what happened? This multiplied by that multiplied by that, and this multiplied by that. Those three terms are written over here, and the last term is written over here. The point is that all of these terms are divisible by a, so we can pull it out. This implies a times a alpha plus some garbage, I don't care what is there inside, this plus bcy beta this is equal to 1, and let me de-highlight the unimportant stuff. Okay. So just by opening the brackets, we see that a times some integer plus bc times some integer is 1. And therefore, the GCD of a and bc is 1. Because if you pick a common divisor of a and bc, it's going to divide 1 because it is going to divide the left-hand side. And therefore, any common divisor has to be equal to 1, showing this equation. So it's a wonderful result, easy in some sense, intuitively easy, but proving this is not easy. I mean, you need something like Bezout's theorem, I would say. I don't think there is any other way. Maybe there is, who knows. But this is the way that I know. Okay. Two more results to go. So exponentiation, this is a consequence of the previous one, really. If GCD of a and b is 1, then GCD of 2 powers of a and b is also 1. Okay? Once you have no common factors between a and b, by exponentiation, magically common factors cannot be created. So let's see why. Proof is, we can use the previous one. So let me just argue for n equals 2. Why should a square and b square have no common factors? So, since GCD of a and b is 1, and since GCD of a and b is 1, I've written the same thing twice for a reason. We apply the previous, we apply the clubbing property. We get that the GCD of a and b square is 1. Correct? So this we get by just the clubbing property. But I will write it like this. I'll do it one more time. So GCD of b square and a is 1. We have this, I've just rewritten it in this way. And GCD of b square and a is 1. Written the same thing twice, and applying the clubbing property, we get GCD of b square a square is 1. And that's it. So that proves it for n equals 2, but you can extend this reasoning for any n. That's great. And let's see an application. So we are saying that if a to the n divides b to the n, then a divides b. That's interesting. The converse was trivial. If a divides b, then clearly that happens. But this direction is interesting. Intuitively, no challenge, but one has to prove it. So the proof is, let's say D is the GCD of A and B. And what we want to do is show that D is equal to A. Let's say A is positive, B is positive, doesn't matter. So we just want to show that D is equal to A. That's what it means to do this. But then, let's say A is D times alpha and B is D times beta. Then GCD of alpha and beta is 1. This is the scaling property. If you divide out by the GCD, what you are left with are relatively prime integers. So make sure you understand this step. If A is GCD times alpha and B is GCD times beta, so you're taking away the GCD, and the numbers that you get are relatively prime. So I hope you follow this. And now, b to the power n divided by a to the power n is what? This is beta to the power n divided by alpha to the power n, because the power of d cancels out. But if alpha and beta are relatively prime, then by the exponentiation property, beta power n and alpha power n are also relatively prime. But this is an integer. This is an integer, correct? This just means that this is an integer and hence this is an integer. But by the fact that alpha power n and beta power n are relatively prime, this implies that alpha power n and beta power n are relatively prime. So let me put an n here by the exponentiation property. Since alpha power n and beta power n are relatively prime, the only way this can be an integer is that alpha power n is 1 and hence alpha is 1, and that's it. If alpha is 1, then d is equal to a. Okay, I hope you followed this. It's important. Okay. And at least one more thing that we want to do today. This is something that I call the dropping property. Suppose A divides BC and A and B are relatively prime, then the only reason A divides BC is that A divides C. You can drop the one that is not interacting with A, so to say. Okay? So, let's see why. So GCD of A and B is 1. We get by Bezout's that this is the case. And we want to prove that A divides C. Let's multiply this equation by C on both sides. So we get C on the right side. We get this. Right, I just multiplied both sides by C. And note that A divides this and A divides that number. A divides BC, right? So A divides that number and hence A divides this. And hence A divides the LHS and hence A divides the RHS. So by Bezout's theorem, this is a zero-line proof. Okay? So very nice. All of these things are intuitively trivial but very difficult to prove directly, at least in my opinion. Okay, let's see an example. So suppose n and r are relatively prime, then we want to show that n divides n choose r. And n choose r, remember, is n choose r. One way to define n choose r, the worst way is by this formula. But the correct way to define n choose r is as the number of subsets, a number of r element subsets of an n element set. Number of subsets of an n element set which have size exactly r. Number of ways of choosing r people out of n given people. Okay, so that's n choose r. And we want to show that if n and r are relatively prime, then n divides n choose r. Okay, so here is a simple property of binomial coefficients. These are called binomial coefficients. So, yeah, so this is equal to, you can just verify that this is equal to n by r, n minus 1 choose r minus 1. It's very easy to verify. Okay. So, what we have is that this is an integer, certainly. This is the number of ways of choosing r people out of n people. So, well known that this is an integer. Therefore, this is an integer. But what are we given? We are given that n and r are relatively prime. So, since this is an integer, it just means that r divides, this means that r divides the product of n and n minus 1 choose r minus 1. Right, that's what it means. Actually, I don't want to do it this way. Okay, I mean, this is correct, but this is not what I wanted to say. So, fine, this is fine. So, what we get from this is r times n choose r is equal to n times this thing, which implies n divides r times n choose r. Right, this is what I wanted to say. Right, all I did was I'm just using this equality to write this by cross multiplication, and therefore n divides the left hand side. But now n and r are relatively prime. That's given to us. Using the dropping property, this immediately gives us n divides n choose r. That's very nice. Okay. So let me end it here. I mean, I could go on. There are other applications to do, but let me end it here and we can continue the next time. All right. So with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.